Okay. Well, actually, what I have in my notes, I think wouldn't take the whole 75 minutes. Probably not anyway. So, um, so how's the homework coming along? Yeah, I asked. Okay. Um, now, for the fourth one, um, how many are doing the coding option? I know Vivian is. Oh, okay. So, and you were already doing the other one. And what about you?
The homeworks.
Oh,
Code.
okay. Yeah. All right. So, I'll look forward to reading whatever you submit. Now,
Yeah, you'll have a little bit of both.
what?
So it'll be nice to have two different things to read instead of all the same thing, right?
Yeah. Variety is good, I think.
Variety's good. Most of the time, until variety is wrong, and then.
Yeah, that's. What is like when I'm grading? It's fine if obviously right answers are obviously wrong. It's when it's not clear, like weird answers. It's like,
and you're like, what were they thinking? Yeah.
Yeah.
And then you have to figure it out.
Yeah. So, so don't do that.
Mystery.
Yeah.
Okay.
And what about? I know the third homework can certainly be a pain. Any questions about that, or?
Yes, the code section.
Okay.
Still working on it.
Okay.
I mean, of course, I haven't enough time to work on it, but it's a work
Okay.
in progress.
Okay. Well, I know.
It's a little progress.
Okay. I know we've talked about that.
Yes, we did. But I mean, I was working on this dissertation thing. So
okay, so you haven't had a chance to. Okay.
But
Yeah.
I would like to figure that out.
Okay. Well, really, yeah, because in the problem 2C that has the code part, where you're solving Laplace's equation on a rectangle, and this with non-homogeneous boundary conditions. So I've given this in out a couple of people already, but so you're solving it like A nu is equal to B, and A comes from like, or actually I'll call that L, and L would be A Kronecker product identity plus I Kronecker product A, where A is a one-dimensional Laplacian matrix. Don't forget the 1 over delta x squared out front. Now for B, so position, based on the way the points that's described in the notes, n minus 1 j plus I corresponds to the point xi yj. So in other words, that particular equation, where the Laplacian stencil is centered around that point. And the way a 5-point stencil for the Laplacian works is on your grid. Here's point ij. So I is the index for x and j is the index for y. So when you go in the x direction, and you have I plus 1j, and then to the right, to the left, I minus 1j. And then for second derivative with respect to y, go down 1, you have ij minus 1, and then up above, ij plus 1. So that's where we get to the term 5-point stencil. So when this point, the center point, ij, is adjacent to a boundary, that's where so one of these points will be on the boundary, one of these four neighbors, and that's, so that point is not included in the left side where your matrix is, it's included on the right side where your boundary is. Or it's included part of the right-hand side vector b. So, so what this means is when I is equal to 1, that's where you deal with the left boundary condition. So u of, so like x equals 0, y, which in this case is equal to 0. When I is equal to n, that is the right boundary. So u of 1y, which is equal to, I think it was y squared, or was it y?
Yeah,
one.
One of them was squared and one wasn't. I can't remember which one.
U of 1y
Yeah.
is equal to y.
Yeah. Okay.
And then u of x1 is x squared.
Yeah, so when j is equal to 1, that is the bottom boundary. So u of x0, which is 0, and then j equals n is the top boundary. U of x1 is equal to x squared. So you can substitute these into this formula for the indices and figure out from there, like if you let, like you plug in I equals n in here, and then j goes from 1 to n, that tells you which elements of b you have to put something in. But keep in mind, you're not just going to put these boundary values because what happens is, for example, let's say I is equal to, okay, let's do something curious. Like I is equal to 2, j is equal to n. So for that equation, you have, with derivative with respect to x, you have u minus 2. Okay, I'm not sure how much was lost, but here's everything I've written today. So at least you're not missing any of that. So what I circled here is where the x squared actually comes into play. And you just have to remember to scale by minus 1 over delta y squared. So all the boundary values are handled in an analogous fashion. I'd say this is one of the most tedious parts of that problem. Actually, Stephanie, you produce a graph, right?
Yeah.
Okay. Yeah. So, and when I saw that, because before you did that, you just tried it without like omega equal 1.
Right. And it ended up being that was about the minimum.
Yeah, that's interesting.
Which
so,
was weird. But yeah.
Yeah,
it's a little off.
Yeah, I wouldn't expect that. And actually, I don't remember what it's supposed to be, but I have a solution somewhere. So.
The actual minimum is probably just a tad past 1, but it was right about 1.
Okay, well, I'm gonna look at my solution, because I did this like a zillion years ago. Of course, it'd be kind of unfortunate if it turned out to be wrong. Okay. Oh, here we go. Oh, what is this? Okay, natural ordering. Okay. Oh, yeah, I got something way different. So that for the optimal.
One of us is wrong. Probably me.
Okay. Interesting. Okay. Yeah, normally for problems like these, the optimal omega turns out to be closer to 2. Okay. And yeah, I was really surprised it only took like 7 iterations. I don't have it listed here as to how many iterations it took. Okay. So, well, in that case, it'd also be a matter of looking at like, well, you did SSOR like component wise, right?
Yeah.
Okay. And I used the matrix form, but all that should be equivalent. So, okay.
probably most important stuff we're writing about today. Yeah, because when I saw that result in your graph, it's like, that's not what I remember. But
Yeah.
okay. Good to know. Well, unfortunately for you. Yeah. Okay. Well, there's still time to figure out what's up with that. Because by Friday, May 12th, so a week from tomorrow, that's when I really need to have everything in. And it can be emailed. That's fine too. Well, for code, that'd be preferable. So however you want to submit it, but I need it by then. And something tells me that weekend's going to be ruined pretty badly because the grades
So
are.
is it okay if we submit the code separately without any explanation in paper?
Actually,
Or you need both?
I want an explanation,
Okay.
like on paper, like so that I'm not wondering why is this missing. So, yeah, you can say like see email or something because I might see the email, but then I'll grade it much later and
Okay.
yeah. Okay, so no one has any particular homework questions? Or? Okay then.
Can you just give like a general hint for all of number 3?
I made that bonus. Except for part A.
You talking about homework 4? Oh yeah, homework 3. Homework 3.
Yeah. Okay. Yeah.
Which one is phone number 3?
Well, B and C.
Oh,
Yeah, and actually, part A is not very involved, but that problem has turned out to be, if you'll pardon the expression, problematic. Because there are certain aspects of solving that are relevant to solving singular systems that we haven't really had a chance to cover. So, if you want to give it a shot, you can, but yeah, it's. You have enough things to do that are a pain in the butt for this class alone, let alone other classes. So, okay. Well, it is a pretty interesting problem, though. Okay. All right. Well, and actually, I was also I wanted to deal with homework questions first to give Abby more time to get here. But
Is she fun?
she told me she is, but running late. So okay. But yeah, this is my last lecture of the semester. There'll be excitement. Okay. Now, a couple times I've brought up singular values, but not said anything about how they're actually computed. And as soon as I get some decent chalk, I will get into that. And now that I've covered how to compute eigenvalues, I'm in a position to do that. And of course, I'm obligated to cover the SED algorithm because my advisor invented it. G developed. Okay. So, fresh memory, this is the singular value decomposition. Or SVD. So A is equal to U sigma V transpose, where A is M by N, U is M by M, V is N by N, and sigma is the same size as A. U is orthogonal, and so is V. And then sigma is diagonal matrix with the singular values that are non-negative along the diagonal. Okay. Now, how we can relate the SVD to things we already know how to compute, to use these properties. So if I describe U as a column partition, and also V, then for all indices for which you actually have both a left and right singular vector, so fresh memory, the U's are the left singular vectors because they come from the left matrix in the SVD, and then V's are the right singular vectors. So you only have both singular vectors for j equals 1, 2, up to p, which I define to be the minimum of m and n. Now, let's see what happens when we multiply these left or right singular vectors by either A or A transpose. So then we get something that we can use. So if I write A times Vj, well, I replace A by a singular value decomposition, U sigma V transpose, and then Vj is a column of V, so that would be Vej. But V is an orthogonal matrix, so V transpose V is identity. So now I have U sigma Ej. But sigma is a diagonal matrix. So sigma Ej is just going to be Ej itself times that singular value. So now I have sigma j Uej, but Uej is just the jth column of U. So I get sigma j Uj. So I'm going to summarize that up here because that was a lot. AVJ is sigma Uj. It's kind of like an eigenvalue relationship, except for eigenvector relationship, vectors of both sides are the same, but here we're not. They're just closely related. Now, if I were to do similar manipulations with A transpose times Uj, so if I did something like this, because the SVD of A transpose is just a transpose of the SVD of A. So by analogous manipulations, what I get for that is sigma j Vj. So multiplying a right singular vector by A or a left singular vector by A transpose gives you that singular value, forgot the j here, that singular value times the opposite kind of singular vector. that has the same singular value. Okay. Now, suppose I use these equations together. So I'll take the first one and multiply by A transpose. So now I have A transpose A Bj would be sigma j A transpose Uj, but A transpose Uj is sigma j Vj. So now when I put all this together, I have A transpose A Bj is equal to sigma j squared Bj. So now I do have the same vector on both sides. That is an eigenvalue-eigenvector relationship. And I can do similar manipulations again, like if I take the second equation and multiply both sides by A, and use these two relationships together in the opposite direction, I have A transpose Uj is sigma squared Uj. So, the right singular vectors are the eigenvectors of A transpose A. The left singular vectors are the eigenvectors of A transpose. And both of these matrices are symmetric. So we have a symmetric eigenvalue problem, which is what you're implementing in the homework 4 if you're choosing that option. So it's nicer than the eigenvalue problem I've been covering. And the eigenvalues are just the squares of the singular values. Okay. So here is an SVD algorithm. Not the SVD algorithm, because this one is stupid, but compared to alternatives. But it's a starting point, and the idea is we'll improve it from here. So what you could do is go ahead and compute, let's say, A transpose A. One of these matrices, doesn't really matter which, but I'll use A transpose A. Then, if you apply the symmetric QR algorithm to B. So that's what I've been covering lately, except because it's symmetric, instead of a Hessenberg reduction, it turns out to be tridiagonal. Also, you don't have to do any of this double implicit shift crap that I've been covering. Just a single shift with a Wilkinson shift, like in homework 4, would be enough. So it's pretty cheap compared to the unsymmetric case. And what you get out of that is this. It's a short decomposition, but the orthogonal matrix that you get is V from the singular value decomposition. Your matrix of eigenvalues is sigma transpose sigma, which is still a diagonal matrix. It has all the singular values squared along the diagonal, and then V transpose. So you have almost everything in the SVD. The only thing that's missing is U. But to get U, use this relationship. Actually, it's this relationship taken with all columns taken together. AV is equal to U sigma. So if you just go ahead and multiply A by V, you know that all the columns of what you get are left singular vectors scaled by singular values that you now have. So you can just divide by the singular values. So in other words, you can say U is equal to AV sigma inverse, or at least for non-zero singular values, you can scale. As for a case of where singular values are 0, what you have, so this would not give you all of the left singular vectors. This would give you U1, U2, up to UR, where R is a rank of A. And then if you take those singular vectors and extend them to a basis, orthonormal basis of Rm, then you'll have a full set of singular vectors. Okay, so yeah, really, just to be more precise here, by V, I really mean V1 up to VR, just those columns. And sigma, I'll have rows and columns 1 through R, just to avoid writing anything terribly wrong on the board. At least for non-zero singular values, you can do this. Okay, and then you extend to a basis. So we at least have an approach to getting the singular value decomposition. But this is not what is used in practice. And the reason why is this step right here. Never do that. Never explicitly, there are many algorithms where A transpose A is called for. You want to try to avoid explicitly computing it, just like it's like a prohibition against computing the inverse. And the reason why is in carrying out that multiplication, there is a loss of information because inevitably, from carrying out this multiplication, there's some round-off error. So information about the entries of A ends up being lost. So if there's a way to get the same information just working directly with A only, then that would be preferable. And that's what my advisor set out to do. So here's how we'll proceed working only on A. Now, in a QR algorithm, what is the first thing that's supposed to be done to A? What's the first step? So for computing eigenvalues, before we do that QR iteration, what are we supposed to do to A? We have to get it to a certain form.
Sure.
Now that's the output of sure decomposition. But
Diagonalize it.
that's the overall goal. But yeah, first step. I covered this on Tuesday and the week before. Yeah, we want to get the Hessenberg form. Now, if it's symmetric, then it's morphed into Hessenberg. We call, what would that be? Hessenberg and symmetric.
Is it Haussmann?
We'll use Householder to get it, but. No, that's later. There's tridiagonal. Yeah, Hessenberg and symmetric is tridiagonal. So we want to do something like that, but again, without explicitly forming A transpose A. So here's what we do. We actually reduce A to upper bidiagonal form. So what we do is we apply House householder transformations on the left, and those are accumulated matrix that I'll call U1, and then different householder transformations on the right that are accumulated matrix I'll call V1, and the output of that is the upper bidiagonal matrix B, and so what I'll do later, I'll call the diagonal elements D1, D2, up to, just to keep things simple, I'm going to assume A is n by n, even though this would apply even if it's not. So D refers to the diagonal entries, and then we have a super diagonal. I'll call those F's. Okay. And these are householder. So the way that this would work is I would use a householder transformation on the left, like to zero out all of the first column except for that first entry. And then I apply a household transformation on the right to zero out all of this part right here. And by working on zeroing this part, but leaving this entry here, whatever it is, or I'm leaving something here, the work I do here involves columns 2 through the end, and therefore does not step on what I did in the first column. So if you were to have to use the same transformations on the right and left, we were trying to do a similarity transformation, we could not get a structure like this, because whatever you do on the left side is undone by what you do on the right. But these transformations are not the same. They have different goals in mind. They're zeroing different kinds of elements. So here we go zeroing elements 2 through n. Here we're zeroing elements 3 through n. So they don't interfere with each other. Now the reason why we do upper bidiagonal form is when you have that, then B transpose B is symmetric and tridiagonal. So in other words, we are implicitly reducing A transpose A to Hessenberg / tridiagonal form without ever actually computing it. So we're computing this like half, if you will, of the of that tridiagonal form. Okay. Now, and I'll call this T for tridiagonal. Now what we could do is proceed with T. Go ahead and form T. This is pretty cheap to multiply these matrices, and then we can apply the symmetric Q algorithm to T. But we are not going to explicitly compute that either, because that would entail the same loss of information that we would get if we would have computed A transpose A at the very beginning. So, not allowed. Okay, so what we're going to do is, oh, surprised I don't have this part in the notes. I can actually show you what the product B transpose B would look like. Even though we're not going to actually have our code computed, it is helpful to know what the entries look like so we can figure out, because what is the goal? We want to reduce, if we were to compute T, we want to reduce it to diagonal form to expose the eigenvalues, which are singular values squared. But so the thing is, we want to manipulate these entries in such a way that whatever happens in here would cause this to be brought closer to diagonal form. So I'll start computing the product. Okay. So by B transpose, so that'll be D's down the diagonal, and then F's below. And then here's B. And then F's that are above. Okay. So example, the 1-1 entry. So I go across the first row, down the first column. I'm only going to get d1 squared. And then the 1-2 entry, across the first row, down the second column. Well, I'm only going to get d1 times f1. Okay. And then, by symmetry, I would have that here, too. Now, for the 2-2 entry, across the second row, down the second column, so that's going to be f1 squared plus d2 squared. And then, let's see, this is tridiagonal, so this entry would be 0. And then row 3, column 2, so I'm going to have, okay, this would be d3. So row 3, column 2, I'd only have 0, f2, d2, or d2, f2. Okay, and then f2 squared, d3 squared. So you can kind of see the pattern. Okay. Now, why this is really helpful is if any fi, any of the super diagonal entries of B ends up being driven to 0 by whatever transformations we make, then decoupling occurs. So for instance, suppose f2 turned out to be 0. Then that would be 0, that would be 0, and this block is cut off from the rest, and the eigenvalue problem decouples. So if we can apply transformations to B to have the effect of making those superdiagonal entries 0, then that would achieve the goal we want of reducing T equals B transpose B to diagonal form. Okay. Now, there's also a possibility that a diagonal entry DI might be reduced to 0 also, and I'll talk about that later. Well, certainly, well, you can see from a product, if the DI becomes 0, again, you're going to get decoupling because you'll have certain off-diagonal entries become 0. Okay. And in fact, what you can do is, let's suppose, in this case, if D2 equals 0, then you have d1 squared, d1 f1, f1 squared, d1 f1. And then this is 0, that's 0, and then the other entry is, here is, well, okay, that entry is still intact. Okay, but again, we have some decoupling. Okay, so we'll aim for making the f's equal to 0, but if we get a d also, we'll gladly take it. Okay. Okay. Now, okay, so in other words, we still want to make this bidiagonal matrix I just erased diagonal if we can. Okay. So, what we do is implicitly apply a QR algorithm step. So in other words, T minus mu identity is equal to QR factorization, and then T is then overwritten with RQ plus mu I, where mu is some appropriately chosen shift. So in this case, it would be like the Wilkinson shift from T, without actually computing T. So it's still B that we're going to work on. So what we do is, first, we compute only the first column of T minus mu identity. So that's going to be, as we can see from over there, it's going to be D1 squared minus mu D1 F1, and then the rest zeros. Okay. Now, from that, we compute the first Gibbons rotation called G1, really G1 transpose because we're going to apply on the left. That would be used to reduce T to upper triangular form. So we have this column, we need to zero out this entry. So all we have to do is compute the Gibbons rotation to work on this 2 vector to zero that element out. And if we were going to compute T minus mu I explicitly and QR factorize it, that's the transformation that G1 that we would use. Okay. Then what we do, once we have a Gibbons rotation in hand, apply G1 transpose to B. So I'm going to call this, okay. Oh, wait a minute. No. I actually apply it on the right. B1 is equal to BG1. Now it seems kind of strange, but here's why. Because T is being overwritten with G1 transpose TG1 if we were to do all this explicitly. But what is T? T is B transpose B. So the new T is BG1 transpose BG1. So that is what I want to compute. Okay. Now, let's see what that looks like. Because B is a bidiagonal matrix. When I finish this QR step, I still want to have a bidiagonal matrix that's hopefully closer to diagonal. But what happens from its Gibbons rotation? So I have my upper bidiagonal matrix, D1, D2, D3, F1, F2, F3, so on. And now I'm performing a Gibbons rotation. Now this Gibbons rotation, when applied to T, is supposed to work on the first 2 rows. But I'm applying it on the right, so it's going to rotate the first 2 columns. So I'm going to have so the sine-cosine pair here, and everything else is going to be identity. Now, when I rotate the first 2 columns of B, can anyone tell me in these two columns, which entries will generally be non-zero in the first two columns after I rotate them using this. Because by rotating columns, each of the first two columns will become a linear combination of those two columns. So what entries are eligible to become non-zero?
1, 1.
Mm-hmm. Well, yeah, that can be non-zero. What else?
1, 2.
Yep.
2, 1.
Yeah. So we get an unwanted non-zero entry here that was not there before. And then the rest of the matrix is still bidiagonal. Okay, so we've done a little damage. So we have to fix that. Now, the easiest way to fix that is to apply another Gibbons rotation on the left now. So I take my BG1 from before, and now I apply another rotation called H1 transpose that rotates rows. So I have some, for H1 transpose, I have some sine, cosine pair, and then identity otherwise. And now I have this, so this is BG1. Whoops. Okay. Now, this Gibbons rotation is explicitly designed to make the 2-1 entry 0. So that's gone. But by rotating those two rows, what unwanted entry, what unwanted non-zero entry are we going to get?
1, 3.
Yeah. So these are okay up here, but now this shows up that we don't want. Okay. So what should we do about that? What can we do about it? And we're going to do something Gibbonsy. Rotate what? Rows, columns, which ones? So first we.
If,
I would say row.
but I need to. Okay, well, no, it's fine.
Okay, let's think about that. If you were to rotate rows, which ones would you rotate? Okay, because basically you need some entry in a neighboring, like if it was row rotations, you need an entry like in a row right above it or right below it to make it 0. So for instance, you actually be candidate would be like this row, but that would cause this entry to become non-zero again. So it goes both ways. Well, you're going to get an unwanted entry no matter what, but that entry, we've just been there. So try something else.
Should be first row, right? We have to move the first row.
No, we don't have to do that.
Unless you rotate the third column and the fourth column, then you
your row.
Yeah. Well, actually, if you rotate the third and fourth column, that would not help because you're using a sentry.
Yeah.
So, okay, but you're getting warmer. So, what can we try instead? And you're going to get an unwanted entry at least, but there's no getting around that. But it is a show of some kind of progress in a way. So if not the fourth column, then what? Well, what would happen in that case is, yeah, we go ahead and rotate these two columns. So now we have H1 transpose B G1 G2 now has this structure. So, okay, so the first column is untouched. The second column, now this is 0. We have an unwanted non-zero entry there. Okay. So, as far as where this bad non-zero entry has been, it started here, but it went here, and now it's here. So, so what can we do next to at least get it out of there?
Multiply by another G series.
What kind of rotation? Okay, and which rows? Yeah, rotate these two rows now. So that'd be H2 transpose H1 transpose B G1 G2. Okay, so the first row is untouched. Second row, now you get an unwanted non-zero entry there. This becomes 0. Everything else is unchanged. So it's bouncing around. It was here, 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 here. So
how many times do you have to repeat to put it?
Peter. Okay, so, all right, you were saying?
I would say.
Well, we have to repeat it again and again till it goes to n, right? If it is n by n.
You are literally chasing this bad element out of a matrix. It's going to keep going, bing, 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 and then it falls off the edge.
But how much does it cost? I mean, how many times we are just multiplying?
Well, okay, so as far as your rotations, like you're rotating first rows 1 and 2, well, actually, first columns 1 and 2, then rows 1 and 2. So you have n-1 rotations of each type, so 2 of those so 2 rotations of each type, so 2 times n-1 rotations altogether. However, this is a bidiagonal matrix with 1 rogue entry in there somewhere. So when you're rotating 2 rows or 2 columns, each one of those entities, row or column, has at most 3 non-zero entries. So order 1 floating point operations per rotation. So the cost is not bad at all. So we have order n flops per implicit QR step. So what happens is we figure out the first transformation that would be applied to T to do a QR algorithm step on it, and then that wrecks the bidiagonal form, and therefore it wrecks the tridiagonal form of T implicitly, and then we fix it. So by the implicit Q theorem, the matrix Q, which would be the product of all of the column rotations, G1, G2 up to Gn-1, is the Q in this QR step of QR factorization of T minus mu identity. So we faked Q just by figuring out the first transformation and then cleaning up its mess. Which took a lot of work because it's like all of a sudden you see a roach, you chase it across the house, and then you finally kill it before it reaches the door. Or maybe, actually, no, you don't kill it at all. You chase it out the door. And, but yeah, at least the cost is reasonable. Okay. So, as we do this, what we'll see is that certain entries along the super diagonal, these Fs, will get smaller and smaller, become 0. So that's when we know there's decoupling. So we want, so we pay attention to, you can think of it as like being like an unreduced portion of B to work with an unreduced tridiagonal block of T to keep reducing it to diagonal form. Okay. So what ends up happening is eventually we have A, which was first reduced to bidiagonal form, U1 transpose A, B1. And then we have this massive accumulation of gibbons row rotations on the left, like these H's over here, and then these gibbons column rotations on the right, converging to a diagonal matrix D. Well, actually, what it converges to is sigma. So that's the that's what we end up getting out of it. Okay, and so then all of this together is your V. All of this together is your U. So you're accumulating transformations to get U and V in the process. So we never had to carry out any matrix-matrix multiplication of A. And we get the whole SVD out of this. Because this is the matrix that will be generated of eigenvectors from the symmetric QR algorithm. That would be the eigenvectors of A transpose A. Or we could think of it the other way, working on AA transpose. Okay, and that's basically the idea. That's the SVD algorithm. So there are a lot of times where you can avoid expensive operations by faking it. We saw that with the QR algorithm. And here again, in both cases, relying on the implicit Q theorem. So there's some really nice results like that that lead to some variating. Okay, I'm not sure how much of my babbling you all missed, those of you who are watching at home, but oh well. Maybe if you're lucky, you missed most of it. But here it is, the SVD algorithm. So I'm just going to shut it now before something else goes wrong. And that's the dang semester. Okay. Yes, I was born the year. That's the last thing I'll say on record on YouTube. I was born the year the SVD algorithm was developed, 1969. So.